أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم، والصلاة والسلام على أشرف خلق الله المرسلين سيدنا محمد وعلى آله وصحبه وسلم. ما زلنا، وربما هذه آخر حلقة في سلسلة نظرية الأوتار مقارنة مع نظريات علي يوسف. هي الحلقة 18، نظرية علي يوسف وظاهرة التشابك الكمي في فضاء EDS أو أنتي دي سيتر. كما قلت ربما تكون هذه آخر حلقة، ولكن يعني إن شاء الله كما تعلمون أنني أتابع المؤتمرات العالمية وأحدث ما توصل إليه العلماء، فربما يعني أزيد هذه السلسلة ببعض الحلقات التي تخبرنا بما توصل آخر ما توصل إليه العلماء في هذا المضمار. لذا أرجو أن تتابعوا الحفظ لهذه السلسلة وتتابعوا آخر التطورات. في هذه الحلقة سنتابع المحاضر يتحدث عن التشابك الكمي في فضاء أنتي دي سيتر سبيس، وهو تشابك كمي من نوع خاص يسمى انتروبي انتانجلمنت أو التشابك كمي للانتروبي، بحيث أنه يعني الانتروبي طبعا يعبر عن الحركة العشوائية، والتشابك الكمي يخبرنا أن هذه الحركة لا يمكن تمييزها، ولهذا لها علاقة بإنفورميشن في الكوانتم انفورميشن أو بلاك هول انفورميشن أو المعلومات في الثقب الأسود. ما فعلته هو أنني وضعت الفرضيات التي وضعتها في التي ذكرتها في الفيديوهات السابقة، قمت بتطبيقها أو تطبيق أجزاء منها، والحمد لله اتفقت مع ما توصل إليه العلماء في هذا الشأن، خصوصا أن الفضاء ثنائي الأبعاد بالنسبة للملاحظ الداخلي نجد أن الانتروبي والانتانجلمنت يقل، أما بالملاحظ الخارجي فالانتروبي والانتانجلمنت يزيد، وبالتالي فضاء أنتي دي سيتر يعتبر فضاء ثنائي الأبعاد بامتياز، ثنائي الأبعاد غير متناظر بامتياز. بالتالي نجد أن الانتروبي والتشابك الكمي يزيدان من خلال ملاحظ موجود في فضاء QFT أو فضاء منكوسكي المسطح. فتعال نشوف ماذا يعني هذا النوع من الاتفاق، وتعال نشوف كيف استدل المحاضر على هذا، وكيف أنا يعني بينت ذلك في هذا الفيديو. تعال ندخل إلى الفيديو.
So first, let me say a few words about the entanglement entropy itself. So this is very, very elementary stuff, even though, but maybe not everybody knows. So let's consider a quantum system, just a general quantum system. Okay. So let's separate the degree of freedom into two parts. Say A plus B. Okay, so A, B together is the whole system. We just separate degree of freedom. So essentially, by definition, the Hilbert space of the system, then we'll have a tensor structure. So the full Hilbert space will be a tensor product over the Hilbert space for the A part and tensored with the Hilbert space in the B part. Okay. Okay, and say, yeah, just consider, of course, in general, we have infinite dimensional system. But if in the case, if you have, say, a finite Hilbert space, say if this is m dimension, this is n dimension, then the total Hilbert space will be m times n dimensional. Okay? And the typical wave function will have the form, will be some sum, say you can write it in some basis in A, and times some wave function writing some basis in B. Okay? And so, yeah, this is actually means that the Hilbert space is a tensor product. It's just your wave function typically have this form. Okay? So we say that AB, so we say that in the states psi, that AB are entangled if psi cannot be written as a simple product. Okay? Rather than a sum of product, and if you just have a single product, okay? So for simple state, it might be easy to see, but if I write a very complicated state with many, I can in principle write the state in some basis which look at the complicated sum, but then maybe in some other basis then will be a simple product. So in general, it's actually hard to tell. Okay, in general, hard to tell, even though it's easy to say, but in general, it's hard to say. So the entanglement entropy, so let me just call it EE just to save space. EE essentially provides a measure to quantify the entanglement between A and B. Okay? Because even in the case which you know this state is entangled state, you may still want to ask how much they entangled, etc. Okay, and entanglement entropy provide a way to quantify it. Okay. So the definition is very simple. So first, we look at the density matrix for the total system. So if the system is in the state psi, then the density matrix for the total system would be just the psi conjugate. Yeah, just psi with itself. Okay, so this is the. So in this density matrix, we just trace out all the degrees freedom in B. Okay. So since the Hilbert space have a tensor product structure, you can always do this. Then what you get is you get the density matrix, and then in this thing. Then here you get the density matrix which only depends on degrees freedom in A. Okay? And then we just calculate the volume entropy corresponding to this rho A. So entanglement entropy is just defined to be the volume entropy associated with this density matrix, rho A. So this rho A is often called the reduced density matrix. Reduced density matrix. Okay. And the volume entropy associated with this reduced density matrix then is defined as entanglement entropy. Okay. So this provides a very good measure because, say, if rho A, say, if SA equal to 0, say if SA equal to 0, from our knowledge of the volume entropy, you can immediately deduce that the SA equal to 0 if only if the rho A, this density matrix is a pure state. It's a pure state. Okay? It's a pure state. And from here, you can also deduce rho A is a pure state. This reduced density matrix comes from this procedure is a pure state only if that psi can be written as a simple product. product. Okay. So this tells you, as whenever SA is non-zero, then you can be sure this state must be unentangled. Okay. Okay, unentangled. So whenever whenever SA is equal to 0, you can be sure this is unentangled. Whenever SA is not equal to 0, and you know for sure this must be A and B must be entangled in this state. Okay, so that's why this is a good measure. Okay, and then the value of SA then will tell you how entangled the system is. Okay. And also you may immediately ask the question, what happens instead of defining row A? Of course, you can also do the same thing. You trace out A to define a row B, and then define the entropy for the row B. Okay? Define the entropy for the OB. But you can easily show for any pure state psi, okay, SA always equal to SP. So it doesn't matter which they're symmetric. So it doesn't matter which one you're looking at. Okay. So this is very easy to prove. Essentially, just following from something called Schmidt decomposition, and you essentially write this state, and in terms of a Schmidt decomposition between the degree freedom of A and B. And then you can show that the row A and row B essentially have the same eigenvalues. And if row A and row B have the same eigenvalues, of course, then the entropy will be the same, because the entropy only depends on their eigenvalues. Okay? Any questions about this? And if row A and row B have the same, then you can show that the row A and row B essentially have the same eigenvalues. And if row A and row B have the same eigenvalues, of course, then the entropy will be the same, because the entropy only depends on their eigenvalues. Okay? Any questions about this? Good. So here is about a mixed state. Let me just about pure state. Let me just say a side remark. Say if AB, the total system, is in a mixed state, okay. So here I always consider it's in the pure state, but suppose it's in the mixed state. Say suppose the system itself is described by a density matrix. So the total system itself is described by a density matrix. Then in general, SA is not equal to SP. Okay. Not only is in general is not equal to SA is not equal to SP, and in such a case, entanglement entropy also contains classical statistical correlations of the mixed state. Okay, of the mixed state. So in addition to quantum correlations. It's almost trivial to see because because suppose here is not a pure state. So here you replace it by a density matrix. And when you trace out B in this density matrix, then of course there's still some original uncertainty in the previous density matrix remaining in A, and then they will come into this entropy. So this entropy, thus defined, will depend on the classical uncertainties, classical statistical uncertainties of your original density matrix. So for mixed state, so that's why for mixed state, the entanglement entropy is not a very good measure of quantum entanglements because it's contaminated by classical statistical information. Okay. But for today, we will only talk about the pure, mostly talk about the pure. Yeah, we will actually talk about in general. Yeah, but I want you to keep this in mind. Okay. So any questions so far? So just to give you a little bit more intuition, let's look at a very simple example to calculate entangled entropy. So let's consider a two-spin system. So let's consider just you have two spins, okay? So this is my A and B, okay? So this have a two-dimensional Hilbert space, this have two-dimensional Hilbert space. Altogether, you have four-dimensional Hilbert space, okay? So for example, so let me consider such a state. So this looks like a complicated state, but actually this can be written as a simple product because you can just written as okay. I hope this notation is for me. It's okay with you. You just have A and B, okay? A spin and B spin. So even though in this basis this is written as say a sum of state, looks like they're entangled, but in fact it's not because then you can write it in terms of a simple product. So this is another entangled state. Okay. So of course, for this simple system, it's very easy to tell. But if you give you a complicated system with many degrees freedom, then become very hard. So and then entanglement entropy become useful. Okay. So now let me give you an example to calculate entanglement entropy. So let's consider a state like this. Okay. So theta is some parameter. So clearly this state is entangled because the you cannot write it as a simple product. So now let's check it. Okay. Now let's check it. So you can look at the full density of the full density matrix of the system. Okay. You just look at this the bra and the cat itself. And then just do the product. Then you get the cosine theta. And the cos terms. Okay. So you just take the batch, take the product with itself, and then let's try to find what's rho A. So you trace out degrees freedom B. So this is our B, the second spin. Okay. Now let's trace out degrees freedom B. Trace out the second spin. So rho A corresponding to we trace out the B in here. So when you trace out the B, you just take the inner product between these two. So these are the same. So this will remain. And so you will have this. And similarly, this one you will have that. These two are the same. So when you take the trace, this is non-zero. But this two will give you 0 because this one is orthogonal to this one, and this spin is orthogonal to that spin. So that's what you get. Okay? And then now you can easily just write down the entropy. Okay. So this is the entanglement entropy for these two states, for this two-spin system, as a general function of this parameter s, theta. So now let's just plot this as a function of s, theta. So clearly this is a periodic function. We only need to go to pi over 2. And then, so you have something like this. Okay, you can easily plot that function. You will see something like this. So when theta equal to 0, this is equal to 0 because this term is 0. This term is also 0 because the cosine theta square is equal to 1. When theta equal to pi over 2, so this term becomes 0, and this term also becomes 0 because log 1 is 0. Okay? So, but there's maximum at pi over 2, pi over 4. So at pi over 4, you have of course you can also go to the pi equal to minus 4. Yeah, you can go to plus minus 4. Yeah, I didn't go to the negative. Yeah, anyway. So this is called the maximal entangled state. Okay? Okay. So this is the maximum entangled. So this is the state which you have the highest entropy. Okay? Any questions so far?
Up, down, down.
Right. That's right. Okay, good. So, so let me also say a few things about the properties of the entanglement entropy. So there are many properties you can derive from here, but I will only say a few important ones. So okay. The one property of the entanglement entropy is so called subadditivity condition. So if you consider the two systems A and B, then you can show that SAB, the entropy for the total system, is smaller than the sum of the separate system. Okay, when I write AB, I mean the combined system. Okay, and this is greater than, say, the difference between them. Okay. So this is so-called the subadditive condition. And intuitively, you can understand, say, if you have entropy of A and entropy of B, you add them together, then it's larger than the entropy of AB because there's some redundancy. There might be some redundancy here, and which is nothing. Yeah, because when you add A, B, and together, there may be some common correlation between them, and so this is greater than that. Okay, intuitively, that's what this inequality means. And also, there's some property called the strong subadditivity condition.
I don't quite understand
Yes.
what SA and SB means. Like,
So this is So this is the entropy for the A. This is the entropy for the B.
but don't we need to to partition system A into two subsystems?
No, you don't. Let me explain my notation. So, so SA means the entropy corresponding to integrate out everything else except A. And SB means you integrate out everything else except B. And SAB means you integrate out everything else except A and B. And this is SAB.
But in our case, A and B is all that there is.
No. And I'm just doing generally. Yeah. Once I have this definition, then so this can be even AB is a total. Yeah. So this can apply both to the case I said earlier. Say if you divide. Yeah. Here I just. So this AB does not have to be the same as that AB. Here I'm just talking about two subsystems. Only two subsystems. Yeah.
So it's like, for example, SA is like I treat A and the supplement of A as two part of the system, and they could have some entanglement. SA just the entanglement entropy of A.
Yeah. SA is entanglement of A with the rest.
Okay.
And SB is entanglement entropy of B between B and the rest. And the SAB is entanglement entropy between the AB together with the rest. Okay? Yes?
Okay, so just want to clarify one thing. So when you say S of A, so you mean we have this whole system, it means that we trace out everything which is not A?
Yeah, that's right. Any more questions about this? So here, when I write those expressions, I assume A and B don't have interceptions, okay? I assume AB don't have interceptions, okay? You can also have the strong subroutine condition. So this is not. So this is pretty easy to prove. If we have time, take 5 minutes to prove. But the strong subroutine, which I'm going to write down. So strong subroutine involving three systems. So now you have to add the three systems, and then greater than ABC. Okay. So again, intuitively, the meaning of those inequalities is clear. So the first inequality just says that I have two systems here, okay? And the sum of these two systems, the entropy of these two systems is greater than the sum between the combined system and the intersection between the two systems. Okay, because C is the intersection between the two, and ABC is the whole thing combined. Okay, and similarly here, it said I have SA and SP. I have two A and B. So I trace out a system outside A, I get entropy for A. I trace out system outside B, I get entropy for B. But this inequality tells that if now you attach A, C to A, and C to B, a common system to both A and B, and then the resulting system will be larger than before. Okay? So if you add something, you increase the entropy. That, of course, intuitively clear, because if you have entropy essentially parameterize your the unknown part of the system, and if you add the third system, and then that just increase your unknown, and then increase your entropy. Okay. 1 second. So this strong subroutine condition is actually very hard to prove. It's very hard to prove. It can get very mathematical, and requires quite some effort to do it. But this one is pretty easy to do. Okay. Yes.
Can you explain truthfully one more time what the first of the two equations? I mean, so for strong subjectivity, what is the first one really?
Yeah. So this means. So look at this as a single system. This as a single system. It means that the sum of these two, the entropy of these two systems, is greater than the sum of the combined system under the intersection. Yeah. Any questions about this? Good. So entangled entropy, yeah, so this concludes a very simple introduction just to the entangled entropy itself.
Does this one have any implications on
Sorry, what do you mean by topology?
because it's like the intersection plus the combined thing.
Yeah, so as a classical entropy, this is a very simple thing. You can easily convince yourself if A, B, C are classical systems and just classical distributions, describe classical probability statistical distributions. And then those things you can just, you can understand this inequality just by drawing this kind of standard diagram corresponding to the different sets. But the quantum mechanically proving those things actually not trivial, not trivial. Quantum mechanically, they no longer come in a very intuitive way. Yeah. Yes?
I was noticing something curious about the last line.
Yeah.
Classically, if A and B are the same, I think the equation would still hold. But quantumly,
It still holds.
doesn't it not hold quantum?
No, this is supposed to hold quantum mechanically.
But the assumption, we're under the assumption that A, B, and C are not, they don't overlap, right?
Yeah.
But I'm saying if A and B are totally overlapping.
No, but this is the for this inequality I'm writing in a way which they are not intersection. You can write them in a way which they intersect, and I'm just writing in this way. So the condition for those, for this particular form, A, B, C are not supposed to intersect.
I'm saying if we set A equals to B,
No, then you cannot use this equation.
Right.
Then you have to write the equation somewhat different way, which apply to the intersection case. You can do it. I'm just choosing to write in the way which they don't intersect.
okay. The thing I wanted to say is we could still keep the bottom equation classically, even if we took.
No, both apply classically. Both are trivial classically. You can understand very easily classically. Just quantum mechanically is no longer trivial. Just quantum mechanics is no longer trivial. And there are and there are various ways you can write those equations. I'm just choosing to write the way which A, B, C they don't intersect, and you can also write the way which just rename them so that they intersect.
Oh, so I will show just that. So this is true for any entangled state we choose.
Any state, yeah, a density matrix, whether it's a pure state or density matrix, it doesn't matter. Yeah. A general statement. Okay, good. So this concludes a short introduction to the entangled entropy itself. And you may know that the entangled entropy actually plays a very important role. Entanglement and entangled entropy itself plays a very important role in quantum information and quantum computing because the quantum entanglement is the kind of quantum correlations which you don't have classically. So that's this EPR paradox and the Bayes inequality and the teleportation, all those things they take advantage of. So yeah, but that's not our main point here. So what I'm going to talk about next is actually entangled entropy is also starting playing a very important role in our understanding of many-body physics and the space-time. Okay? Oh. So now let's talk about the entanglement entropy in many-body systems, in quantum many-body systems. So I hope you are familiar with this word, many-body systems. It's just a system of large number of particles or a large number of constituents. So quantum field theory is a many-body system. Any quantum field theory is a many-body system, okay? But this also includes many other lattice systems which condensed matter people use, which are not necessary quantum field theory. It can be written as a quantum field theory, okay? So now let's again consider just a simplified case. Let's consider a system which compose A and B, say A plus B, okay? And then I will say some trivial statements. So if H is HA plus HB, so now we talk about the Hamiltonian. So far I'm not using actually many body system. Right now what I'm talking about applied to generic system, okay? So if the Hamiltonian is actually just a direct sum of the Hamiltonian for A and the Hamiltonian for B, if they don't coupled, then of course the energy eigenstate or in particular the ground state is unentangled. So you just find the ground state of each system, and then that's the ground state of the total system, okay? And also, in general, if you start with an initial state which is unentangled, with an initial state which is unentangled, it will remain unentangled, okay? So if you start with an unentangled state, you evolve it using this Hamiltonian, of course it will just act on the specific part, and then it will remain unentangled, okay? And now let's consider we have H equal to HA, HB, but now they also have interactions between A and B. So A and B are now coupled, okay? Then in general, we can just repeat what we said here. Then the ground state is now entangled, okay? And now if you start with the initial state, even if you start with the initial unentangled state, will becomes entangled under Hamiltonian evolution. Okay, on the time evolution. So in general, we will expect. So just based on this general expectation, so you would expect the ground state of a typical many-body system will be actually rather entangled. Okay. Okay, will be rather entangled, unless the Hamiltonian factorized into all free particles. Okay. Not to factorize into the Hilbert space at each point, okay, for each degree of freedom. Okay, but now let's talk about the many-body systems we are interested in. Okay, so they're either typical condensed matter systems or quantum field series, okay? So in typical condensed matter systems, we face this problem. So in typical or generic condensed matter systems or quantum field theory or quantum field series, okay, in general, no matter how you divide A and B, so generic HAB is non-zero, okay? But not only is H on B is non-zero, it's in general, in typical HAB, so the whole Hamiltonian, including HAB, is local. Okay, and this is a very important concept. It's local. By local, we mean the following. For example, let me give you an example. So, for example, so one of the very important condensed matter system is so-called Heisenberg model. So essentially, you have the Hamiltonian. So you can see the lattice in whatever dimension you are interested in whatever kind of lattice you are. Just at each lattice, there's a spin. Okay. So consider you have a lattice of spins, and then you have Lewis label interactions between the neighboring spins. So sum over nearest neighbors. Okay. So you can imagine you have a lattice system, and each point on the lattice, you have a spin, and each spin is interact only with the spins nearby. Okay. So this is a local interaction. Okay. So by local interaction, means that the only direct coupled to the spin finite distance away from it. Okay. And so this is an example of a local system. And all our QFTs are local system. So all our QFT are local system. For example, let me just write down the phi-4 theory. For example, phi-4 theory.
طبعا هنا علينا نعرف أنه local Hamiltonian أو local system يعني في نظرية يوسف هو كثافة عالية للهاملتونيان في حيز ضيق أو في حيز يعتمد رد فعل الفضاء ثنائي الأبعاد على هذه الكثافة وهذا الحيز، أو كما يقولوا كثافة الهاملتونيان density. وبالتالي كل ما يخرج من هذه الأمر يعني تعتبر هذه قاعدة، وكل من يخرج منها من المفترض أن تكون مشابها تماما الفيزياء التي تخرج من يعني ما يقوله المحاضر، والفيزياء التي تخرج من نظريتي مفترض تكون متشابهة تماما.
Then phi at each point, so now you have to go back to your first state of your quantum field theory, which when we emphasize locality. So the phi evaluated at each point now is independent degree freedom, okay? And the quantum field theory is a Hilbert space of a tensor product of those degree freedom, okay? And the form of the Lagrangian, so if you discretize it, and this only involving coupling between the neighboring point, because the derivative, this only depends on the second derivative. And this only depends on the value of phi at the single point. So the typical quantum field theory, if you have, as far as you have finite number of derivatives, it's all local. It's all local interactions. Yeah, it's all local. Okay. So in other words, in this kind of systems, let me go back here. So this is very important. In other words, in this kind of systems, say let me just imagine, so let me just say this box is the whole thing. It's the whole, whatever space I live in, okay? And I divide it into A, B, okay? So this tells you that for typical condensed matter system or conformal field or quantum field series, the HAB is only supported. So let me call this epsilon. So that tells that HAB is only supported near the boundary between A and B, because there's only local interactions. So the part of the Hamiltonian which directly couple A and B only within this part. And this epsilon is either the lattice spacing, is order of lattice spacing, which in the case of a lattice system, or in the quantum field theory, it would be your short distance cutoff. So if you try to discretize your field theory, and then this will be a short distance cutoff. Okay? So similarly, I can consider other shape of A. So suppose I consider a circular A. And then again, the part of which HAB is only supported in the region between these two dashed lines. And those dashed lines should be considered to be very close to the A. Okay? I'm just drawing it big. But this should be just short distance cutoff. Okay? And again, the HAB is only supported in here. So this is a feature, or important feature, which you have a local Hamiltonian. Okay? It turns out this actually, let me just write one more word. So HAB only involves degrees freedom near the boundary of A. Okay? So this means the boundary of A. Okay? So this turns out to have very, very important implications. Okay? The fact that the Hamiltonian is local and that they only directly mediate coupling between degrees freedom near the boundary of A turns out to have very important consequences. So what I find, so now I'm just telling you the result, which is a result that have been accumulated for many, many years, since the early 90s. So then what I find, in the ground state, of a local Hamiltonian in general, you may construct some kind of evil counterexamples. But in general, in the ground state of a local Hamiltonian, take any region A, just choose any region A, you integrate out degrees freedom outside of it. Okay. So let me emphasize the important point. Let me just pause to emphasize the important point, which is only implicit in what I'm saying here. So when you, in this definition of the entanglement entropy, which I just erased, you just need to have a partition of degrees freedom between A and B. The way you partition it does not matter. Okay. How you partition it does not matter. You can partition whatever way you want. But for typical this kind of lattice system, or for quantum field theory, there's a very lateral partition. And the partition is just based on the locality. It's just based on the degrees freedom at each point. Okay, you just factorize your Hilbert space in terms of degrees freedom at each point. Of course, in the lattice system, it's obvious. You have a spin at each lattice. And for quantum field theory, and you just factorize your degrees freedom at each point, you factorize them. Okay, and so this provides a natural, this locality provides a natural partition of your Hilbert space, of your degrees freedom, and when we talk about then when we talk about A and B, we always talk about in terms of the space location, okay? And then it's natural to talk about the partition in terms of the just geometric locations. Okay, is this point clear? Yeah, I just want to emphasize this point. So then you find that in general, for the ground state of a local Hamiltonian satisfies so-called area law, is that the leading term of the entanglement entropy is given by the area of the boundary of A. This applies no matter which dimension you are in generic dimensions, and divided by a short distance cutoff, or the lattice spacing. There's some number. So SA is a dimensionless number. So area, so we consider a d-dimensional theory, so d-dimensional system. Then the spatial dimension will be d minus 1. And then you go to the boundary of some region, the boundary of region A, then that would be a d minus 2 dimensional surface. And then this would be the area of that surface. Okay? So this may cover a dimensionless number. And then you can have some prefactor here, which depend on your systems. Okay? So this formula tells you a very important physics. So this formula tells you very important physics. It tells you that generically, if you in such kind of systems, AB are entangled, but the entanglement between AB between A or its complement, which I just call A and B, are dominated by short range entanglement near boundary of A, where this HAB is supported. Okay? So this is also very intuitive once you know the answer. Because we emphasized that HAB only coupled to degrees freedom nearby. And then when you look at the ground state, you find the degrees freedom, most of the degrees freedom here don't entangle with B. Only degrees freedom near the boundary of A are entangled with B because of this interaction. Okay? Just say this local interaction directly leads to the entanglement between the degrees freedom nearby. And those degrees freedom, they're far away. They might be entangled, but they're not dominant. Okay? So I put many dots here. So included in those dots are, say, possible long-range entanglements. Yeah, because when you find the ground state, you really have to extremize the energy of the total system. You don't only look at this small part. So there's always some kind of long-range entanglement beyond this HAB. But this formula tells you that this short distance entanglement dominates. Okay? Yes?
Some question. So in QFT in general, like the standard model, there's really all the interactions pretty local, I believe. But in string theory, are there any like non-local interactions that can occur? Are there any Lagrangians with non-local?
Yeah, then depend on the scale. In string theory, when we say non-local, it's non-local at the alpha prime scale. And that alpha prime can perfectly be our short distance cutoff here. When I talk about local, non-local, I'm talking about infinite versus finite. For example, here when I talk about whether this is a local system, I don't have to have a nearest neighbor. As far as in this lattice, this point only directly coupled to the finite distance neighbor, and this considered local. Hamiltonian. But from quantum field theory point of view, this might be considered non-local. You see what I mean? Depend on your scale. Yeah.
So one thing. So is there anything that appears in, say, in string theory which is non-local at any scale, or is the non-locality just some?
Yeah. So the string theory itself does not give you that kind of non-locality, but the black hole may.
Oh, interesting.
The black hole seems to give you some kind of non-locality which we don't fully understand. So that's why black hole is so puzzling. And the perturbative string theory, you are non-local in the scale of alpha prime. If it's alpha prime sufficient small, it's like local theory. And even alpha prime is big. If you look at very large distance, it's still like local. Yeah, but black hole can make things very non-local at very long distance. Yeah, so that's the tricky thing about black hole. Okay. So this is something which was very interesting, and first discovered in the early 90s. But in hindsight, it's very intuitive. Okay, in hindsight, it's very intuitive. So even though this formula, even though this term is universal, but this coefficient is actually highly non-universal. Normally, by saying universal, we mean something which is common to different systems. So this coefficient actually depends on the details of individual systems. So if you calculate for Heisenberg model, or if you calculate for the free scalar field theory or free fermion theory, and then this coefficient in general is different and depends on how you define your cutoff. Okay. So even though this formula is universal, but those prefactors are actually highly non-universal. So let me just.
لماذا قال الكوفيشنت أو الرقم الفاكتور هو يعني مخصوص أو يعتمد على نوع هو يعني شيء مخصوص وليس عام، لأنه هنا الفضاء ثنائي الأبعاد. طيب خلينا نشرح الأمر بطريقة نظرية يوسف. الاريا كما ذكر هي الاريا، هي المنطقة المحصورة بين A و B، وهي تعتبر في الباوندريز بالنسبة ل A، وهذه الاريا فيها كثافة عالية للهاملتونيان. تعال نفترض ذلك على القطف اللي هي إبسلون سي دي ناقص 2. هذه الإبسلون هي الأريحية التي يعطيها فضاء ثنائي الأبعاد لنفسه، وهو الطريقة الذي يدخن فيها فضاء ثنائي الأبعاد الفضاء تحت هذا الهاملتونيان الكثيف الذي يوجد داخله. طيب لهذا نجد أن الرقم اللي يعتبر كوفيشنت، هذا الرقم يعتمد على ماذا؟ يعتمد على نوع الهاملتونيان، ويعتمد على الطاقة، أو نقول كثافة الطاقة نوعها، سواء كانت طاقة كهرومغناطيسية أو طاقة جاذبية. نحن عندنا نوعين من الطاقات، طاقة كهرومغناطيسية وطاقة جاذبية، وعندنا أبعاد. شيء مهم جدا، عندنا أبعاد. فيعتمد هذا الرقم على الطاقة وعلى الأبعاد أو كثافة الطاقة بس. يعني إذا أردت أن تجمل الأمر يعتمد على كثافة الطاقة، نوع الطاقة وكثافتها فقط، لأن كثافة الطاقة تشمل الأبعاد. ونوع الطاقة عندنا طاقتين، طاقة كهرومغناطيسية وطاقة جاذبية. والطاقة الجاذبية في الأبعاد الصغيرة تعتبر أقوى للفضاء ثنائي الأبعاد من الطاقة الكهرومغناطيسية، وبالتالي هذا الرقم يعتمد على نوع الطاقة. إذا كانت طاقة كهرومغناطيسية هذا الرقم سيكون الانتروبي سيكون صغيرا. إذا كانت طاقة جاذبية هذا الرقم سيكون كبيرا. يعني الانتروبي يلعب دورا كبيرا في طاقة جاذبية أكثر من الطاقة الكهرومغناطيسية. دعونا نضرب مثال في ذلك. في تفاعلات الهيدرونات الكبير تحصل التفاعلات في مساحة صغيرة جدا. هذه المساحة تندمج فيها الطاقات والكتل، ويراها الفضاء ثنائي الأبعاد غير متناظر في شكل طاقة. طيب ماذا يفعل؟ يطردها بحيث يوسع القطف اللي هو إبسلون دي أس سي ناقص 2، إبسلون أس دي ناقص 2. التوزيع هذا يولد مجموعة ضخمة من الكتل. هذه الكتل تعتمد على الرقم، على الرقم الكوفيشنت. والانتروبي، هذا الانتروبي هو طبعا يعتمد على الانتروبي، يكون عالي جدا. لماذا؟ لأنه هناك هاملتونيان عالي جدا أو كثافة عالية جدا للطاقة في مساحة ضيقة جدا جدا، فبالتالي الانتروبي يكون عالي جدا جدا سواء كان للA ولا الB. قل للA والرقم سيكون هذا الكونفيشن سيكون عالي جدا. أثناء سير هذه المحاضرة نركز على هذه النقطة لأنها مهمة في نظرية علي يوسف. طبعا هذه المحاضرة هي نوع من التطويل، لأن الانتروبي أصلا من الأمور الصعبة جدا للفهم. فليس الانتاجلمنت، أقصد الانتاجلمنت، من الأمور الصعبة جدا للفهم. طيب ماذا يحدث؟ النظرية علي يوسف فسرت الأمر بكل سهولة وتركت الأمر للفضاء صناعي الأبعاد، لكن بالنسبة للQFT والفيزياء المعاصرة الأمر صعب. يعني قبل قليل الأستاذ ذكر أن بالنسبة للثقب الأسود فإن الانتاج أو النون لوكاليتي كبيرة جدا، تأخذ مساحة كبيرة جدا. لماذا تأخذ مساحة كبيرة جدا؟ لأنه كما ذكرت أن الانتاجمنت يزيد مع ماذا؟ يذهب للفرضيات. تعال نذهب للفرضيات التي كتبتها لنعرف أن الانتاجمنت يزيد مع ماذا؟ طيب نجد هنا في الفرضيات بالنسبة للملاحظ الداخلي نجد أن الفضاء ثنائي الأبعاد يقلل ما يسمى بالتشابك الكمي أو الانتاجمنت. طيب بالنسبة للملاحظ الخارجي نجد أن يزيد الفضاء ثنائي الأبعاد، يزيد ما يسمى بالتشابك الكمي أو الانتاجمنت. طيب بالنسبة للثقب الأسود نجد أن البيئة الداخلية هذه يحاول أن يحافظ عليها الفضاء ثنائي الأبعاد غير متناظر، فبالتالي بالنسبة للملاحظ الخارجي يرى أن الانتاجمنت يزيد بمعنى أنه كلما تقربنا من الثقب الأسود زاد الانتاجمنت أو النون لوكاليتي، لأنه هي يمكن أن تكون مرادفة للانتاجمنت، فيزيد النون لوكاليتي ويزيد الانتاجمنت من أفق الحدث وربما قبل أفق الحدث. طيب هذا الأمر شبيه بماذا؟ أنا طبعا ذكرت مرارا وتكرارا أن الفضاء الداخلي للثقب الأسود شبيه بماذا؟ شبيه بالفضاء الخالي من الكتل، شبيه بالفضاء عند الأبعاد الصغيرة. فعند الأبعاد الصغيرة أبعاد الإلكترون والبروتون نجد أن الانتاجمنت عالي جدا وأن النون لوكاليتي أيضا عالي. أيضا الفضاء الخالي من الكتل تماما، يعني الفضاء البعيد من المجرات، أيضا نجد أن النون لوكاليتي عالي والفضاء والانتاجمنت عالي. مجمل هذا أو كخلاصة نقول أنه كلما زاد معدلات تدفق الزمان والمكان كلما زاد الانتاجمنت. هذه هي الخلاصة. أي مكان يزيد فيه معدلات تدفق الزمان والمكان يزيد فيه الانتاجمنت. نكون نحن غير قادرين، لأن معدلات تدفق الزمان والمكان زادت، نكون غير قادرين على تتبع الحركة نسبة لمعدلات تدفق. يعني هناك سيكون هناك فرق في معدلات تدفق الزمان والمكان في ذلك الفضاء وفضاءنا نحن. هذا يستخلص منه عدم قدرة التتبع بالنسبة لذلك الفضاء. ربما تكون الرؤية وضحت. هذه الفرضيات سنطبق هذه الفرضيات في هذه المحاضرة.
Highly non-universal. So, but the excitement, partial excitement, there are many things people are excited about entanglement entropy. This is one thing, this area law. Because the area law is nice, because then because then that then this can be used as a distinguishing properties of a ground state. Okay, if you go to highly excited state, then you find the generic degree of freedom inside A and B will be entangled. And when you go to highly excited, but only in the ground state, somehow only near the boundary they're entangled. Okay, this is also makes sense because if you go to very high energies, then you can excite degrees of freedom very far away from HAB. Then of course everything will be entangled. Okay.
So just one other quick question. So why is it that? So why are you dividing by epsilon? Okay, because
No, this is dimensionless number. Make it into a dimensionless number, and this is only short distance information here. This lattice spatial short distance cutoff.
right. The only reason I ask is that intuitively it seems that the entropy should be sort of proportional to like this like thin volume around the boundary, but that doesn't. I mean, okay, I don't know.
No, you have to make it into a dimensionless number. You have to proportion to the area. Then, so there's a very simple way to understand that thing.
Okay.
So the area divided by lattice spacing. So what is this guy? This is roughly a lattice volume.
Yes.
Lattice area on the a lattice area on the surface. So essentially, this tells you how many degrees of freedom are lying on that boundary.
Okay, interesting.
Yeah. Okay. So is it clear? Okay, I think I'm spending too much time on this. Anyway, so excitement in the last decade about the many excitement about the entangled entropy in the last decade. One thing is about this behavior, then you can use it as a characterization of the ground state. But a lot of excitement about this thing is on those dots. So people actually find that the subleading term, some excitement. I'm just saying. From last decade, people discovered that the subleading terms in the entangled entropy, other than this area term, which comes in from non-range entanglement. So this captures the short range entanglement. From the long range entanglement, can actually provide important characterizations of a system. Okay. So let me just mention two examples. So I'll be a little bit fast because we are a little bit.
طبعا هذا أيضا نتفق مع نظريتي عند الهاير تيرمز، وهذا ما ذكرته قبل قليل أن الهاير تيرمز لابد أن يكون يؤثر أو يتأثر تماما بالنظام الذي نحن بصدده. كما ذكرت أنه قوة الجاذبية أكبر من قوات الكهرومغناطيسية، لكن ممكن أن نقول أننا نستبعد قوى الجاذبية بأي شكل كان بأي آلية وننظر القوى الكهرومغناطيسية كيف تؤثر على الفضاء ثنائي الأبعاد. وبالتالي الهاير تيرمز هذه تعتمد على النوع بشدة، تعتمد على النوع بشدة وتعتمد على الكثافة بشدة أو النوع، يعني نقول النوع بشدة، لأن هناك أنواع تأثر بدرجة أكبر. يعني مثلا نمسك القوى الأساسية الأربعة. في نظريتي القوى الأساسية الأربعة طبعا القوة الجاذبية هي الأكبر، بعدها القوة الكهرومغناطيسية. بالنسبة للقوى النووية الضعيفة والقوية هي عبارة عن دمج بين الجاذبية والكهرومغناطيسية. القوى النووية القوية هي عبارة عن قوة كهرومغناطيسية وقليل جدا من الجاذبية، لماذا؟ لأنه عندما نتعامل مع البروتونات نجد أن السلايس الفضاء مقسم بالنسبة للقوى الكهرومغناطيسية أكبر من قوى الجاذبية، لأن قوى الجاذبية تؤثر بقوة. طيب، وبالتالي القوى النووية القوية تعتمد أكبر شيء على القوى الكهرومغناطيسية، والكوانتيزيشن السبيس كوانتيزيشن بالنسبة للقوى الكهرومغناطيسية وقليل بالنسبة للقوى الجاذبية. عندما نذهب إلى طبعا حدود السترونج والقوى النووية القوية حدود 10 أس ناقص 16. إذا مشينا إلى القوة الضعيفة، قوة نووية ضعيفة، حدود 10 أس ناقص 18. لذلك نجد أنها تعتمد على الجاذبية بدرجة أكبر من الكهرومغناطيسية، لكن الكهرومغناطيسية أيضا موجودة لكن تعتمد على الجاذبية، ولهذا تخرج لنا ما يسمى بنيوترينو. النيوترينو يخرج باعتماد القوى الجاذبية وليس لديه شحنة. وأيضا تخرج لنا في النشاط الإشعاعي تخرج لنا الإلكترون والبوزيترون، هي تعتبر من القوى الكهرومغناطيسية وأيضا الجاذبية، لأن الإلكترون والبوزيترون لديهم كتلة. أما النيوترينو لديه كتلة ضعيفة جدا جدا لكن ليس لديه شحنة. ربما يكون لديه شحنة ضعيفة جدا جدا، لكن هنا نجد أكثر شيء في النشاط الإشعاعي هو يعتمد على الكتل. لماذا؟ جسيم ألفا فيه 4 كتل، 2 بروتون 2 نيوترون، وانظر للنيوترون ليس فيه شحنة، وبالتالي هذا يعطينا اعتماد أكبر على الكتلة. الانشطار طبعا يعتبر من القوى النووية القوية وليس الضعيفة، لكن إذا الانشطار والله الانشطار يعتمد على القوى النووية الضعيفة أيضا للأبعاد الصغيرة أيضا. نعم، لكن نجد تأثير في الجسيمات في العناصر الضخمة، نجد تأثير البروتونات أكبر من تأثير تأثير الشحنة أكبر من تأثير الكتلة. لهذا نجد نقول أن تأثير الشحنة في انشطار مثلا زي اليورانيوم يكون كبيرا. نعم، وقد تحدثت في هذا في فيديو سابق، تعال نذهب إليه. لماذا أنوية ذرات العناصر متماسكة رغم عن أنها لديها عدد بروتونات ذات شحنة موجبة؟ هذا الفيديو الذي مدته 31 دقيقة 52 ثانية، ويندرج تحت نفس السلسلة string theory الحلقة الخامسة. هذا الفيديو يتحدث بعمق بالإضافة لفيديوهات أخرى بعمق عن طاقة الربط النووي، ويمكنكم الذهاب إليه. وأيضا اذهبوا لسلسلة الملاك يقبح في التفاصيل، بالذات آخر 3 فيديوهات تتحدث بعمق في هذا الأمر. طيب، نرجع مرة أخرى.
On the break for the last day.
When you say it like that.
Okay, good. Good. Okay, thanks. So just quickly talk about 2 examples because I want to talk about the holographic case. So the first is something called a topological, can be used to characterize so-called a topological order. in 2 plus 1 dimension. Okay, in 2 plus 1 dimension. So since 90s, late 80s and the 90s, people discovered that they are, say, if you look at the typical gapped system, so when we say a gapped system, means that that system between the ground state and the first excited state have a finite energy gap, okay? So our general understanding for a gapped system is that in the ground state, because you have a finite gap, and at sufficiently low energies, you essentially cannot excite anything. Yeah, because sufficient low energy, because you have a finite gap to the first excited state, you cannot excite anything. So essentially, when you look at the correlation functions, we can look at the observables. They all only have short-range correlations. Then they cannot have long-range correlation because there's nothing to propagate you to long distance. And because long distance require massless degrees of freedom, and because you have a gap, you don't have such massless degrees of freedom. Okay? So the typical conventional idea about the gap system is that all correlations should be short-ranged. And so this is a conventional wisdom, but in the late 80s and early 90s, our colleague Xiaogang Wen, he introduced this notion of a topological ordered system based on quantum Hall effect, fractional quantum Hall effect. So he actually reasoned that there can be gapped systems, even though I have a finite gap, but in the ground state actually contain long-range correlations, non-trivial long-range correlations. And those long-range correlations cannot be seen using the standard observables. So if you're using the standard observables, say correlation functions of local operators, etc., you don't see them. You only see the short-range correlations. And those long-range correlations are topological in nature. You have to see it in some subtle ways. And then in the 80s, exactly in the late 80s, early 90s, he was trying to argue in some indirect way to argue there's such kind of subtle correlations. But then around 2000, maybe around 2005, then he realized actually you can see it very easily directly from the ground state wave function. You just calculate the entangled entropy. So entangled entropy, you always have this, so this is a 2 plus 1 system, and then the boundary is just a line, okay? So essentially you just have a boundary, some number, the length of the boundary, say divided by your cutoff. But then turns out for this kind of topological ordered system, there's a finite constant as a sub-leading term. And this finite constant is independent the shape of A and independent of length of A, independent of whatever A is purely topological in nature. And so if you have a trivially gap system, then this gamma will be 0. Say, look at the free massive scalar field, or free, then this gamma will be 0. But for those topological ordered systems, this gamma will be non-zero, and it tells you actually there's long-range correlation, which are encoded in this correlation in the entangled entropy. Okay, because this cannot come from the local thing, because this does not depend on the shape of A, does not depend on the length of A, does not depend on anything of A. Okay, so this is really topological in nature. Tells you this can only be some long-range subtle correlation, which is only captured by this entangled entropy rather than by the standard correlation functions. Okay, so this is one discovery.
طبعا هذه ربما أفسرها أنا نظريتي بمعدلات تدفق الزمان والمكان، وهذه المعدلات هي التي تجعل يعني تخلق شيء من النون لوكاليتي، وبالتالي يعني هذه correlations تصبح مرتبطة بالتوبولوجي بسبب معدلات تدفق الزمان والمكان والاختلاف في معدلات تدفق الزمان والمكان. طبعا هناك اختلاف في معدلات. أول شيء معدلات تدفق الزمان والمكان تعتمد على الأبعاد، كبرت الأبعاد ناقصت معدلات التدفق صغيرة الأبعاد كبرت معدلات تدفق. هذا بالإضافة إلى أنه الفرق بين معدلات تدفق الزمان والمكان أيضا يتغير بوجود الكتلة. يعني الكتلة هي التي تعمل على تغيير معدلات تدفق المكان والزمان من خلال معادلة المترية اللي هو التي رأيناها x على c t يساوي نص مضروب في 1 ناقص اللوغاريتم. هذه المعادلة تقول لنا أن النسبة بين x و t تعتمد على الكتلة. بالتالي نجد أن x و t كل ما زاد الكتلة كل ما تقاربت مع بعضها البعض. وأيضا الكتلة غير ثابتة، الكتلة تعتمد على المرجع الملاحظ، بالتالي أيضا تدخل في هذا الأمر.
which generated lot of interest in the entangled entropy, because now this can be used to define the phases. Okay, you can actually define non-trivial phases using this number. Okay, and so this is first thing. A second thing. So this is about in the condensed matter systems. In quantum field theories, this can be used to characterize the number of degrees freedom of a QFT. Okay. Again, this is a long story, but I don't have time. So let me just tell you a short story. So first, let me look at 1 + 1 dimension, a CFT. Okay. So for 1 + 1 dimensional CFT, an important quantity is so-called central charge. So have you all heard of central charge, or not really? Okay. It just say, imagine you have a 1 + 1 dimensional CFT. And for each CFT, you can define a number, a single number, which is called the central charge. And this central charge is very important because it controls the asymptotic density of state of the system. So if you look at the system, go to very high energies, and the density of state is essentially controlled by this number C. Okay? So essentially, C can be used to characterize the number of your degrees freedom. And C will appear in many other places, but I don't have time to explain. But anyway, just there's something called the central charge, which is can be used to characterize number of degrees freedom of system. And turns out, if you look at the entanglement entropy for 1 + 1 dimensional system, for 1 + 1 dimensional CFT, so in 1 + 1 dimension, you only have a line, the spatial direction. So then let's take A just to be a segment of length L. Okay? Then you find when you integrate out everything else, the entanglement entropy for the A given by C divided by 3 log L divided by epsilon. Again, epsilon is a short distance cutoff. And the C is your central charge. So you see that your entanglement entropy, first you notice that that formula becomes degenerate when you go to the 2 dimensions, t equal to 1 + 1 dimension. So in 1 + 1 dimension is replaced by something like this. You have log epsilon. Okay. So the key important thing is that now the prefactor, because of the log, the prefactor is actually reversal, and it's actually controlled by the central charge. So that tells you from the entanglement entropy, you can actually read the central charge and actually read what is the number of degrees freedom of the system. And this, so for many, so the fact that the central charge in the 1 + 1 dimensional CFT, it captures the number of degrees freedom was known before people think about the entanglement entropy, etc. But turns out, and many people spend many years trying to how to generalize this concept to higher dimensional theories. Okay? And turned out it's very hard to generalize. People didn't really know how to do it. But now we know, because you can just generalize the entangled entropy to higher dimensions. And then you find the same kind of central charge which appear. You find again, things can be defined as analog of the central charge in 1 + 1 dimension appears in the entangled entropy in the higher dimensions. And then they can be used to characterize the number of degrees freedom. Okay? And so in some sense, the entangled entropy really provide a unified way to think about this central charge and to characterize number of degrees freedom across all dimensions. Across all dimensions. And yeah, so this is a key formula. Actually, first realized by our friend Frank Wilczek, and when they study a free field theory, and then people later generalized to show this actually works for any CFT. And at the beginning, yeah. Good. So now finally we can talk about holographic entangled entropy with those preparations. Okay?
طبعا هنا هو ما دام قال لك 1,1 بالنسبة للجروب ثيوري، يعني ربما يكون هذه له علاقة بالفضاء ثنائي الأبعاد غير متناظر، لأن الفضاء ثنائي الأبعاد غير متناظر لديه بعد أكبر من الآخر، فكلما زاد ال المسافة زاد الانتروبي، يعني زاد التشابك الكمي، وبالتالي زادت جهلنا بهذا الفضاء وعدم التناظر. هذا طبعا هذا يصب في موضوع مصطلح عدم التناظر، فنقول أنه ثنائي الأبعاد غير متناظر، فبالتالي إنه نجد أن ال تزيد من عدم التناظر، لكن السي هذه السي سنتر تشارج أنا يعني لم أفهمها جيدا، هل هي تزيد أم تنقص؟ يعني المفترض إنه الكتلة تعمل على إنقاص عدم التناظر وتعمل على زيادة التناظر، وزيادة التناظر يعني زيادة دقة القياسات وما إلى ذلك. فالسي أنا لم أفهمه، هو ذكر أنها سنتر تشارج، فربما نقول أنه ربما إذا كان هناك تشارج في الفضاء، تشارج في مساحة صغيرة، التشارج تعمل نعم التشارج تعمل على زيادة التناظر، ولكن أيضا تعمل شيء معين، وهي تعمل على تقاصر الفضاء حوله، يعني السبيسينج في الفضاء يزيد ينقص كلما تقربنا من الشحنة. جميل. ربما يصب في هذا الأمر، لأنه إذا رأينا داخل الشحنة الأمر ينعكس تماما، فإن الشحنة تعمل على زيادة معدلات تدفق الزمان داخلها. يعني إنسان حاول يرى أو ملاحظ حاول يرى داخل الشحنة، فإنه سيكون عنده معدل تدفق الفضاء نسبة لصغر الأبعاد، بالإضافة لمعدل تدفق الفضاء الناتج من داخل الشحنة، وبالتالي ربما يكون من هذا المنطلق، الله أعلم، لكن يمكن العلماء أن يبحثوا في هذا.
Study a free field theory, and then people later generalized to show this actually works for any CFT. And at the beginning, yeah. Actually, first realized, and yeah, so this is a key formula. Actually, first realized by our friend Frank Wilczek, and when they study a free field theory, and then people later generalized to show this actually works for any CFT. And at the beginning, yeah, they can be used. But so the fact that the central charge in the 1+1 dimensional CFT captures the number of degrees freedom was known before people think about the entanglement entropy, etc. But turns out, and many people spend many years trying to how to generalize this concept to higher dimensional theories. Okay. And turned out it's very hard to generalize. People didn't really know how to do it. But now we know, because you can just generalize the entangled entropy to higher dimensions. And then you find the same kind of central charge which appear. You find again, things can be defined as analog of the central charge in 1+1 dimension appears in the entangled entropy in the higher dimensions. And then they can be used to characterize the number of degrees freedom. Okay? And so in some sense, the entangled entropy really provide a unified.
طيب في الفرضيات التي رأيناها قبل قليل، ذكرت أنه بالنسبة للفضاء الداخلي، الملاحظة الداخل الفضاء ثنائي الأبعاد، فإن درجات الحرية تقل، وبالنسبة للفضاء الخارجي الملاحظ الخارجي، أنا ذكرت أن الفضاء أنه درجات الحرية تقل أيضا، لكن في الحقيقة يعني إذا زاد الهاملتونيان تزيد درجات الحرية على ما أظن. هذا يعني يمكن للعلماء أن يبحثوا في هذا الأمر، أنه للملاحظ الخارجي وهو ينظر الفضاء الثنائي الأبعاد غير متناظر داخل الفضاء الثنائي الأبعاد غير متناظر، فإنه يرى ماذا؟ فإنه مفترض يرى الهاملتونيان. طبعا الهاملتونيان يزيد نسبة لزيادة معدلات تدفق الزمان والمكان، وبالتالي مفترض درجات الحرية تزيد على هذا. الله أعلم، يمكن العلماء أن يبحثوا في هذا.
Way to think about this essential charge and to characterize number diffusion across all dimensions. Across all dimensions. And yeah, so this is a key formula.
لكن زيادة معدلات زيادة الدايمنشنز يعني قادم من زيادة الكتلة، وزيادة الكتلة تزيد معدلات تزيد درجات الحرية. طبعا زيادة الأبعاد طبعا تزيد درجات الحرية، هذا أمر معروف. في زيادة الأبعاد تزيد درجات الحرية.
Actually, first realized by our friend Frank Wilczek, and when they study a free field theory, and then people later generalized to show this actually works for any CFT. And at the beginning, yeah. Good. So now finally we can talk about holographic entangled entropy with those preparations. Okay. So this just gives you some taste that actually why we are actually interested in the entangled entropy, and why this actually not only people in quantum computing or quantum information people are interested in it, people doing condensed matter, people doing quantum field theory are also interested in it. Okay. And now people doing string theory are also interested in it because of this holographic entanglement entropy. Okay. So suppose we have a CFT.
طبعا قبل أن يدخل في الهولوغرافيك برنسبل دعنا نتفق على أشياء. أنه داخل البلك فإن السيطرة يكون للفضاء ثنائي الأبعاد غير متناظر، وبالتالي الانتروبي الانتانجلمنت مفترض أن يزيد. إذا كان الانتانجلمنت حسب ما فهمته يعبر عن جهلنا بالفضاء، فإن الانتانجلمنت يزيد بمعدلات تدفق الزمان والمكان، وبالتالي يزيد في البلك وينقص في الباوندريز، لأنه هناك الجسيمات. طبعا ينقص يعني يختفي، لأننا نحن نعلم أن كيو اف تي أو جسيمات الكيو اف تي فيها انتانجلمنت عالي، لكن ينقص بمعنى أنه يكون أقل من البلك. وهذا واضح أنه نجد أن السترينجز داخل البلك لديه طاقة عالية. طبعا الأمر يرتبط بالطاقة، لأنه حسب كتاب الحلقة 50 وحسب نظريتي أو فرضيتي في الكوفارينت برينسيبل، نجد أن الانتقال من فضاء عادي إلى فضاء كثيف هي مثل فضاء داخل الثقب الأسود، وانتقال من فضاء مينكوفسكي إلى فضاء داخل الثقب الأسود، فإن الكتلة تنقص والطاقة تزيد. زادت الطاقة يعني زاد اللوكاليتي. لكن هناك شيء آخر يحصل في الثقب الأسود، وهو أن حجم الجسيمات تنقص، حجم الأجسام تنقص. أيضا صغر الأبعاد هذه أيضا يزيد من الانتانجلمنت. طيب إذن في البلك مفترض أن الانتانجلمنت يزيد، وفي الباوندريز يقل قليلا الانتانجلمنت. تعال نتأكد من هذه المعلومة في هذا
T, say T-dimensional CFT with a gravity dual, say dual to some theory in D+1 dimensional anti-de Sitter space-time. So let me give you a region A. How do I find the entangled? What is the counterpart of this entangled entropy on the gravity side? Okay. So this is the question. So yeah, let me just draw this figure. Suppose this is the box again, represent the total system, and then let's carve out the region A. Then the question, what does this translate into in the gravity side? Okay, so now the boundary you have some region A, and z equal to 0. Okay. So, so this question, in some sense, is difficult because it's not like other questions we talked about before. So Wilson loop, partition function, you can say the partition function have to be the same. Those things appear to be natural. Here, there's no natural thing you can think about because you cannot define entangled entropy as a partition function. You cannot entangled entropy have to involve in so-called trace out the degrees of freedom, then take the logarithm, etc. It's a highly non-local and complicated procedure. And it's not obvious how you would define on the gravity side. How would you guess on the gravity side? Okay, so it's quite remarkable. And the Rutagalagi, they just made a guess, and then it worked. Okay, so the proposal is just find the minimal area surface, let me call gamma A, which extends in the back, extends into the back, and with the boundary of A as the boundary. Okay, you first find this surface, and then you say the entangled entropy for A is just the area of this gamma A divided by 4g Newton. Okay, so this is the Rutagalagi. So the idea is that you find a minimal surface, a surface of a minimal area, which going into the back but ending on the boundary of A. Okay, so this is your gamma A. And you find such a minimal surface, then you divide by 4g Newton. Okay.
طبعا بالقسم على 4g نيوتن نجد أن داخل البلك نيوتن ثابت نيوتن يؤول إلى زيرو، وهذا يصحح يعني يصدق ما ذكرته أن الانتروبي داخل البلك هو أعلى من الباوندريز، لكن تعال نتأكد أكثر.
So let me just mention one thing. So let me just note just to a simple thing. Just emphasize again, the A of the boundary, this is d minus 2 dimensional. Okay? And A and the gamma A are all d minus 1 dimensional. So this is d minus 2 dimension is what we said before, because A is just a region in your spatial section. So A is a d minus 1 dimensional, and the boundary A will be d minus 2 dimensional. And the gamma A would be a surface which ending on the boundary of A. This ends on that thing. So this is also d minus 1 dimensional. Okay? And this is d minus 1 dimensional, so this area have dimension d minus 1, and that's precisely the dimension of G Newton in the d plus 1 dimensional anti-de Sitter space-time, and then this is a dimensionless number. Okay, because we need the SA to be dimensionless. So, so you can say this is a very difficult gas. You can also say this is a very simple gas. Because clearly this formula is motivated by the black hole entropy formula. You may say, black hole entropy is something divided by 4gn. maybe this entanglement entropy is also entropy. Maybe it's also something divided by 4gn. And maybe some surface divided by 4gn. And then the special surface will be the minimal surface. So in some sense, it's a very naive guess. And you could say it's a very simple guess. But as I said, it's also a very difficult guess because essentially, other than that, you don't have other starting points. Okay? Yes?
So the one question I don't totally understand is, okay, so we have A in the CFT. Where do we know exactly where to place A in the ADS? Because it's not, I mean...
This is a good question. Yeah, this is a question actually I'm going to say next.
Okay.
Yeah, but let me just emphasize that. So when we talk about A, we're always talking about the constant time slice because you have to specify some time. And actually, when we consider the ground state or typical state, which does not depend on time, and then actually does not matter which slice you choose. Yeah, just choose a time slice, and then you specify the region A. Because to talk about degree of freedom, you only talk about in the spatial section, right? And you just, yeah, so A. So here, so if you have, say, if you have a ground state or have any state which does not depend on time, then the gravity side also does not depend on time. It's a time-dependent geometry. So the time slicing in the field theory naturally extends in the gravity side. And so in the gravity side, this surface will be in the constant time slicing, which you go to the gravity side, okay?
So that's one other thing. But still, when you're in the CFT and the ADS, I mean, okay, so I know that we like to think one existing on the boundary of the other, right? But that doesn't, but how does, well, but that's just sort of an abstraction, right?
No, that you should really consider as a real thing.
Okay.
Real stuff. Yeah. If you just think that as an abstraction, then you miss lots of intuition. Okay. Because use that as a genuine boundary give you a lot of intuition. And then many things become very natural.
Okay.
Yeah, many things become very natural. Yes?
So comparing to the other formula that also has area of the boundary of A,
Yeah.
All this tells us is just, it kind of helps us count the number of degrees of freedom in the CFT. So all it tells us is basically the epsilon on the denominator?
No, they have complete different dimension.
Yeah.
No, these have one higher dimension.
So that's another.
The gamma I, no, this is not strange at all because they're not supposed to be the same. No, this is that's it should be. So this is the d minus 1 dimensional, and that is the d minus 2 dimensional. It's just completely different.
Well, right, but they're not, like, there is something the same about them, so.
No, there's something to say about them, but these two have completely different physics. So these have close analog with black hole physics. And yeah, I don't think they're motivated by that formula. I think they're motivated by the black hole formula. And the people also try to connect that formula to the black hole formula. That's another story. Anyway, it doesn't matter. OK, good. So this is a gas. Yes?
So is this result only valid for the ground state of the CFT?
No, this is valid, yeah, for the time-independent state. Any state that's not involved with time.
The thing I don't understand is, on the side of the CFT, there's this state that you give as an input to calculate the entanglement entropy.
Yeah.
And what's the corresponding thing on the ADS side?
ADS side is the corresponding geometry. So we said before, each state on the field theory should correspond to some geometry with normalizable modes. Yeah, so it's the corresponding geometry. And the ground state, then this will be just pure ADS. And if you look at the finite temperature state, then this will be the black hole. And then if you are able to construct some other geometry corresponding to some other state, you can use that.
I imagine this entanglement entropy is independent on which state we choose for CFT.
No. Of course it depends. No, this formula does not, but the geometry does. Geometry does. This is a minimal surface in whatever box geometry.
But the region, after we choose the region, we can choose any state in the CFT.
Yes.
And as a minimal surface is independent on which state we choose.
Of course, will depend on which state you choose. Because each state corresponding to a different geometry, and the minimal surface depends on your geometry. So each state, so remember our previously, the state on the CFT side is mapped to the geometry with normalizable boundary conditions, with normalizable modes. Yeah, anyway, just let me say just geometry. So a state with a geometry. If you have a different state, you have a different geometry. But by definition, all these geometry be asymptotically ADS. So when you go to a boundary, they should all be asymptotically ADS. So that's what means to have normalizable mode excited. Okay? Yes?
So this entropy formula takes into account the entropy of gravitational excitations in ADS, if you think about it that way. But black hole entropy...
No. Let's try not to jump too fast. And I think we are trying to extrapolate too fast. This formula is supposed to calculate the entanglement entropy in the field theory side in the large N limit and the large lambda toward coupling limit. And we can talk about the gravitational interpretation later, but this formula is about the field theory entanglement entropy. Okay? Good. Any other questions? Okay, good. So there are many support of it. So this is a rule of the game. You make a guess, then you do a check. If the check worked, then that give you confidence, and then you do another check until you find it fail. Okay? And if you do sufficient number of checks, then people believed you. Then people will believe you, and everybody starting checking it, and then sooner or later we will see whether this fail or work. Anyway, so this is nice because this is simple to compute. Because finding a minimal surface on the gravity side is in some sense, it's a straightforward mathematical.
طبعا نحن نعلم أن داخل الثقب الأسود الانترابي عالي. نعم، داخل الثقب الأسود الانترابي عالي، وبالتالي فرضية تصبح صحيحة لأن الانترابي عالي داخل الثقب الأسود. ولكن تعال نتأكد أكثر.
Problem, conceptually, even though technically may not be simple, but it's a straightforward conceptually. Anyway, so you can use this to calculate many quantities. Yeah, so yeah, let me just say the support of this. Yeah, let me just say it in words, just to save time. So you can check. So the first thing you should check is that this satisfies the strong subadditive condition, which we wrote down earlier, because that's a very non-trivial condition, should be satisfied by the entropy. So first you should check that. Because if it violates that, then this proposal is gone. Okay? And then another thing is that you can try to use to reproduce all the known behavior we know about entanglement entropy. For example, this behavior, and this behavior, this area law, etc. Okay? And then once you build up confidence by checking all those known results, and then you can try to derive new results and to see whether new results make physical sense. Okay? Yeah, so essentially that's how it works. And this is nice also at the technical level because the entanglement entropy is something very hard to compute. I don't know, you guys may not have experience of calculating entanglement entropy, but ask Frank Wilczek. He was one of the first people to do in some free field theory. Even for free field theory, people could mostly do it in 1+1 dimension. Going beyond 1+1 dimension, free scalar field theory in 2+1 dimension or 3+1 dimension, for some simple region like a circle or sphere, you have to do numerical calculation. You have to discretize the field theory to do very massive numerical calculation. It's not easy to compute. It's not easy to compute. But this guy is actually easy to compute in comparison. So this guy at the technical level provides a huge convenience to calculate many things. Okay? Yeah, so this is a side remark. So now let's just do some do some calculations. So first, let me show that this is actually satisfies strong subadditivity. So remember the formula we had before. SAC, yeah, unfortunately I erased it. Okay, so this is one of the inequalities. So I will just draw it using 1 + 1 dimension because it's easy to draw. But a similar thing can be easily generalized to higher dimension. So now let's look at just a line in 1 + 1 dimension. So let's can call this region A, this region C, this region B. You can also make them separate, doesn't matter. You can also make them separate. It's easy to work out. So I'm just giving you one cases, okay? So suppose the minimal surface for the AC region is like this, and the minimal surface for the BC region will be like this, right? Okay, some minimal surface like that. Okay. So let me call this curve gamma AC, and this curve gamma BC. Okay. I could not find a color chalk today, so I did not have the color chalk. So let me see whether this chalk works. Oh, is this a color chalk? Yes. So now let me define two other surfaces. Let me call this one gamma 1, and this one gamma 2. In principle, I should use two different chalks for them. Okay? You think it looks like something? Okay. Anyway, so we have gamma AC plus gamma BC equal to gamma 1 plus gamma 2 because I just so gamma AC this is length, gamma BC is equal to gamma 1 plus gamma 2. Okay? Gamma 2. And then just from the definition of the minimal surface, then the gamma 1 must be greater than gamma C, okay, in terms of the length. Because the minimal surface associated with C must be the minimal area, so must be smaller than gamma 1. And the area of gamma 2 must be greater than gamma ABC, because the gamma 2 is the boundary is the ABC, and then the gamma 2 must be greater than gamma ABC because this is supposed to be the minimal surface. Okay? So now we conclude. That gamma AC plus gamma BC greater than gamma ABC plus gamma C. Okay? And then this translates into that formula. Okay? Very simple and elegant proof. Very simple and elegant proof. And now you can prove another inequality. You can prove another inequality, which is SAC plus SBC greater than SA and SB. So now I will define another surface. Okay? So now, let me just redraw it. A, C, B. So I have AC like this, I have BC like this. And now let me call this one gamma 1 tilde, this one gamma 2 tilde. Yeah, this one gamma 2 tilde. This is annoying. Okay? And again, gamma AB, gamma AC plus gamma BC equal to gamma 1 tilde plus gamma 2 tilde. Okay? But gamma 1 tilde ends in A, gamma 2 tilde ends in B. That means gamma 1 tilde must be greater than gamma A, and gamma 2 tilde must be greater than gamma B. Okay? So now you show that gamma AC plus gamma BC is greater than gamma A plus gamma B. Okay? So this is very easy. So this is very simple and elegant. So if you want to really to be impressed by this, I urge you to look at the proof of the strong subjectivity itself in the, say, in some textbook or in the original papers, it's actually highly non-trivial. Using some double concave functions, etc., is quite highly involved. Okay. Okay. So this is a great confidence boost that this satisfies the strong subjectivity condition. Okay. So now let's look at another one. Let's try to reproduce this formula. Let's try to do a simple calculation to reproduce this formula. So this formula is supposed to be true for any CFT. Okay. Then this should be also apply for the holographic CFT, and to check whether this formula works. Okay. Yeah, the reason you would like to choose an example which is new, but this example is the simplest, so that's the reason I choose this example, even though it just reproduced all the results. Okay. So let's say, so now let's look at entangled entropy of 1 + 1 dimensional CFT. So here now you have a CFT 1 + 1 should be dual to the ADS3. Do some theory in ADS3. So ds square. So let's only look at the vacuum. Then we just work with ADS3. So let me write down the ADS metric, ADS3 metric. So Tx is the boundary directions. Okay. So as I said that each CFT is characterized by a central charge. Central charge. And you can obtain central charge from various different ways. And that we are not, again, from the holograph, you can try to express the central charge in terms of gravity quantities. And there's many ways to derive it that will not go through that calculation. So let me just write down the results. So for the holographic CFTs, the central charge is related to the gravity quantity by 3r divided by 2 g Newton. Okay. So this is the result which I just quote. Okay, I will not derive it for you. Yeah, but you can derive it using many different ways. So for CFT dual gravity in ADS3, its central charge is given by 3r, which is the ADS radius, divided by 2 times the Newton constant. And the Newton constant in 3 dimension has length dimension 1, so this is the dimension is number. Okay. Dimension is number. So now let's calculate the entanglement entropy. Okay, using that formula. So this now reduced to a calculation very similar to our Wilson loop calculation. So let's call this L divided by 2. So let's call this x direction. So this is the z direction. So this L divided by 2. This minus L divided by 2. This region is A. Then we need to find a curve, because this is now 1 + 1 dimensions. 1 dimension, so we need to find the curve which ends on this segment of A. Okay? So is this clear? So this is x direction, and so this is 0, x equal to 0. Yes? Okay? So what we need to find is to find the minimal surface connect between these 2 points. Okay? Or a minimal curve, minimal length curve to connect between these 2 points. So as we said before, we should look at the constant time slice, because this is the vacuum which is time independent. Let's just look at the constant time slice. Then on the constant time slice, the metric become, so in this space, the metric just become r squared divided by z squared, because the time does not change. Okay? So now if I treat the x as a function of z, and then this will become, so this curve, let me parameterize x as a function of z, then this just becomes r squared divided by z squared, 1 plus x prime squared dz squared. Okay? And in particular, so this is the dl squared. So the length of the curve square would be just parameterized by this guy. Okay? And we have to satisfy the boundary condition. Yeah, by symmetry, we only need to consider, say, the right half, okay? Because it's symmetric. So we impose the boundary condition that the x z equal to 0 is L divided by 2, okay? To consider the right half. So now you can just write down the entanglement entropy now. So SA will be 1 over 4gn. So I integrate half of the curve. So let me just call here z is equal to 0. Let me call this point z0. So I just integrate from 0 to z0. Z0 we will find out when you find out this minimal length curve. So this will be rz dz. Then just take the square root of this guy, square root of 1 over x prime square. Okay, so this is the length, and the times 2, because we only consider, this is half of it. Okay? And now you extremize it, then you find the minimal length curve, and then you plug the solution here, then you find the action. But actually, we don't need to extremize it because this is a well-known problem. And this is called a Poincare disk. So this is a prototype of a two-dimensional hyperbolic space. And the minimal length curve in such a hyperbolic space is maybe 16th century problem. No, maybe, yeah, I don't know, actually, maybe 17th century. Anyway, so the answer is actually well known, but you can also easily work out yourself. So the result is actually, this is just exactly a circle, okay? Exactly a half circle. So the answer, so that's actually a half circle. This means that x equal to, the half circle with radius L divided by 2. So this is just become L squared divided by 4 minus z squared. Okay? In particular, z0 corresponding to the point which x equal to 0, just L divided by 2. So now you just plug this into here. Just plugging it here. Let me just write it a little bit fast because we are a little bit out of time. So you plug this in, and then you can scale the z out. Okay, you can scale z to be still the L divided by 2 factor out. Okay, let me just scale it. You can rewrite the integral as follows. So after that scaling, say do z scale with L divided by 2z, do this scaling, okay? Then you find this expression become 2r, 4gn. And the upper limit become 1. And the lower limit, you see, when you plug this in, actually the lower limit is divergent because there's 1 over z here, okay? That we always need to put the cutoff. And also this divergence is expected because of the below that here. It depends on short distance cutoff, it will be divergent, okay? So we need to put the short distance cutoff here. So let me put here to epsilon. Then this will be 2 epsilon divided by L when I do this scaling, okay? And then you have dz, z, 1 minus z squared. So the integral will reduce to something like this. And now you can evaluate this integral trivially. Then you find, then in the epsilon goes to 0 limit. Then you find the one term survives, 2r divided by 4gn log L divided by epsilon. Okay? So now let's try to rewrite in terms of this c. You rewrite in terms of c. So this is 1/3 3r divided by 2gn log L divided by epsilon. And so this is precisely that formula, c divided by 3 log L of epsilon. Okay. So, and this result, it just comes from the minimal surface in the hyperbolic space is a circle. Okay, and it takes lots of effort to calculate this thing, even you do a free field theory calculation. And okay, yeah, but in gravity you can do it very easily. So now let me just mention quickly mention it. What happens if you do it at finite temperature? So you can also do it at finite temperature. So since we are out of time, so I will be doing it a little bit fast. So first doing at finite temperature is easier. So let me say finite T. And then I will connect to the black hole entropy, okay? I will show that this formula actually reduced to the black hole entropy in some limits. Okay. So for this purpose, actually, it's easier to consider CFT on the circle. Okay. So when the CFT on the circle, the boundary will be a circle because this is 1 + 1 dimension. So remember, in the global ADS, it's like a cylinder, and the boundary, and in the 1 + 1 dimensional case, and the boundary is just really a circle, and this is the bulk. Okay. And at the finite temperature, you put the black hole there. So let me just put the black hole here. Okay. Just put the black hole there. So now you can ask the following question. So now let's consider some region A. So let's consider A is very small. Okay, you can work out the minimal surface. So exactly the same as our Wilson loop story. So you find the minimal surface, but if A is sufficiently small, then the geometry around here is still ADS, and then you just get a minimal surface around here. So small deformation from the vacuum behavior. Okay, so we make A larger and larger. So this Z0 depends on this Z0 depends on L. If you make L larger and larger, this zero will deeper in the bulk. So if you make A larger, so this will go more to the bulk, and then will be deformed, and then we'll see the black hole geometry, etc. Okay. But now you can ask the question: how about if I make A to be larger, this region to be A, to be larger than half of the size of the circle? So the minimal surface should be able to be smoothly deformed back into A. So now you have to do something like this. Turns out the minimal surface want to go around the horizon, and then doing something like this. Okay, doing something like this.
Why not do the other round?
No, it's because the other one, because A is like this, and if you do something like this, and then it cannot be deformed back into A smoothly without crossing black hole. Okay. Yes.
But there could be like a phase jump or something at some point when one surface becomes longer than or smaller.
No. In this situation, there's no that thing. Okay, it's something like this. Now, if you make A even longer, eventually let's take the A even longer, and then will be something like this. Yeah, because you always want to hug near the horizon. And eventually, if you make A to be tiny, then will become something like this. You have something close on the horizon, then you have something like this. Okay, it's roughly something like this. Maybe I should just, is it clear to you? It doesn't matter. So now let's consider. Anyway, let me just draw this again. It actually does matter. Sorry. So let's take A to be very small. Here, take A to be very big. Just this part to be very small. So we'll find that we'll go like this. Anyway, something like this. Okay, we want to hug the black hole. And eventually, when these 2 points shrink, so take A to be the total region. Okay, take A to be the total space. What do you get? Then what you see that the minimal surface essentially is just essentially a surface, a hug around the horizon. Okay. And this is a precise black hole formula, because then this is precise black hole formula. And this is the situation you expect it to be black hole formula. Because if you take the A to be the whole space, then rho A is just equal to the rho of the whole system. Okay? And then SA, by definition, is just equal to the S of the whole system. And this is just a thermal density, a thermal entropy. And this is given by the black hole formula. Okay? This is given by the black hole formula. And this is given by the black hole. So you find in these special cases, actually, you recover the black hole formula. Okay? So I have some small things. Yeah, we can talk a little bit more, but I think we'll skip it. You can also show that actually for general dimensions, you always recover the area law without the details of the geometry. Because no matter what kind of dimension you look at, and the typical state, which will be normalizable geometry, when you approach the ADS, when you approach the boundary, it's always like ADS, okay? And then you find in higher dimension, it's always like this. It's like when this minimal surface is close to the boundary, it becomes perpendicular to the boundary. Here it's a circle, then of course it's perpendicular to the boundary. But you see this feature actually generalized to higher dimensions, to any dimensions. So what you see is that in the general dimension, a minimal surface will be just near the boundary, will be just perpendicularly going down from everywhere. Okay? And then from that, you can show that you always have the area law from the boundary from this behavior. Okay, from this behavior, you always have the area law. So this can be give you exercise for yourself. Yeah. So let me just finish by saying a couple of philosophical remarks. Then we finish. So this RT formula is really remarkable because it's actually, as I said, technically provides a very simple way to calculate entanglement entropy. But actually, conceptually, it's even more profound because it tells you that the space-time is related to the entanglement. Because it relates something which is very subtle from the field theory side. Because this essay, as we said, is you have to do some complicated procedure to trace out degrees of freedom, take the log, etc. And that turns out to be related to the geometry in a very simple way. So essentially, you see that the entanglement is just captured by the space-time. And in particular, in some sense, you can say the geometry is essentially equal to the quantum information. Okay. So this is very exciting, also from the gravity perspective, because it tells you if you really understand this duality, then you can actually, using the quantum information of the field theory, to understand the subtle things about the geometry. Okay? Yeah, it just tells you the geometry is actually equal to the quantum information. Okay.
طبعا هذا يفسر ما قلته عن معدلات تدفق الزمان والمكان عند الأبعاد الصغيرة يعني زيادة المعدلات عند الأبعاد الصغيرة ونقصان المعدلات عند الأبعاد الكبيرة. هذا ما يفسر هذه الدواليتي.
So for many years, actually not that many years. So previously we have people doing quantum information, and we have people doing condensed matter, which is the quantum, say, many body system. kinesmatic or QCD. So this is kind of quantum many-body. And then we have people doing black hole, string theory, and gravity. So they are all very different fields. But now they're all connected by this holographic duality. Somehow essentially connect all of them. So now we essentially just see a unified picture, a unified a paradigm to understand all quantum systems, including quantum systems without gravity, with gravity, etc. Okay? So I will stop here.
طبعا هذا الكلام يعني أنه الانتروبي داخل الثقب الأسود أعلى من الانتروبي خارج الثقب الأسود، وهذا واضح من الدائرة الذي رسمها. تعالوا نشوف الدائرة. هذه أنه عندما تكون A صغيرة، الحدود على الباوندرز تكون صغيرة، يكون الدائرة على تحيط كامل بالثقب الأسود، وبالتالي وفي الحدود في الباوندر تكون صغيرة، نصف القطر صغير، وهنا دائرة كبيرة، وبالتالي الدائرة أكبر من نصف القطر، بالتالي الانتروبي بالنسبة للثقب الأسود أعلى من الانتروبي خارج الثقب الأسود. طبعا هو اعتبر الخارج الثقب الأسود هو خارج أفق الحدث، هذا ما عمل لي إشكالية. والثقب الدائرة الصغيرة هذه بها 3 خطوط تعتبر الثقب الأسود ومن أفق الحدث. طبعا الأمر يختلف إذا اعتبرنا من أفق الحدث قبل أفق الحدث، الأمر يختلف لأنه يزيد التايم دايليشن. يعني إنسان من الخارج ينظر قبل أفق الحدث يزيد التايم دايليشن، وزيادة التايم دايليشن طبعا نرى الأجسام تقف عند أفق الحدث، يعني بسبب التايم دايليشن والريد شيفت. لو نجد الأجسام تقف عند أفق الحدث يتم مشاهدتها وتقف عند الأفق، تطبع عند الأفق، وهي في الأخير يكون دخلت داخل الثقب الأسود، لكن بالنسبة للملاحظ الخارجي يجدها واقفة. وهذا يعني أن ماذا؟ يعني أن الانتروبي واضح جدا، أو الانتانجلمنت لا يوجد انتانجلمنت لأنه اللوكاليتي واضح جدا، والمادة والجسم عندك يعني نحن نراه. وعكس تماما بالنسبة لل طبعا الأمر أيضا ينطبق لمن لإنسان ملاحظ موجود على جسم الثقب الأسود وينظر من الداخل، ينظر عند أفق الحدث، أيضا يرى اللوكاليتي ويرى أنه الجسم يعني واضح جدا مطبوع في الداخل على أفق الحدث، لأنه هو معدلات تدفق الزمن عنده عالية، هو موجود في جسم الثقب الأسود. والجسم الآخر الملاحظ وليس الملاحظ يعني مفعول به موجود على أفق الحدث. هنا يجد ماذا؟ نجد أن معدلات تدفق زمنه هو أعلى من معدلات تدفق الجسم الموجود على أفق الحدث، فبالتالي هو يرى أفق الحدث واضح جدا. والعكس أيضا صحيح، أن الجسم على أفق الحدث لا يستطيع أن يرى الملاحظ الموجود جوا في جسم الثقب الأسود. لماذا؟ لأنه معدلات تدفق الزمن عالية جدا عند جسم أو مركز، نقول مركز الثقب الأسود، على عكس على أفق الحدث فإن معدلاته تكون أقل. الأمر أيضا ينطبق إلى ملاحظ الخارجي يرى الجسم عندما يسقط داخل الثقب الأسود ويستطيع أن يراه، فإنه يرى معدلات تدفق زمن عالية جدا جدا، وبالتالي لن يرى مكانه في الحقيقة، حتى لو يعني إلا يجيب أجهزة حديثة جدا جدا لا يستطيع أن يرى مكانه، وأيضا لا يستطيع أن يراه بذات نفسه. لهذا يرى سوادا، يعني السواد الذي نراه في الثقب الأسود إذا تخطينا أفق الحدث، هذا سواد ناتج من ماذا؟ هذا سواد ناتج من معدلات تدفق الزمان والمكان، هي معدلات تدفق عالية جدا جدا، وبالتالي الأحداث هناك تسير بسرعة عالية جدا، وبالإضافة إلى أنه الكتلة تقمع، يحصل لها سبريشن، تقمع بحيث تنقص أبعادها. كل ذلك يجعل أنه لا نستطيع أن نرى داخل الثقب الأسود. ولكن أعتقد أنه الأستاذ والمحاضر اتفق معي في هذا، أنه الانتانجلمنت انتروبي انتانجلمنت في داخل ال ADS أكبر من في الخارج، وبالتالي هذا يتفق معي في أنه الفضاء داخل ال ADS يشبه تماما الفضاء داخل الثقب الأسود، وبالتالي يمكن تطبيق الثقب الأسود في نظرية الهولوغرافي بكل سهولة، أو يمكن تطبيق نظرية الهولوغرافي في الثقب الأسود بكل سهولة. وبالتالي نستطيع أن نرى، نستطيع أن نقيس، نعمل قياسات لنظرية السترينج ثيوري من خلال ملاحظاتنا للثقب الأسود. بهذا يكون انتهينا من هذه السلسلة، الحمد لله والشكر لله، وهذه آخر حلقة. ولكن إذا وجدت هناك مستجدات فيما يتعلق بالسترينج ثيوري، خصوصا أنا أشاهد في اليوتيوب مؤتمرات عالمية، فأي مستجدات سأضيفها لهذه الحلقة مباشرة، فكونوا متابعين لهذه السلسلة، يعني أضيفها لهذه السلسلة مباشرة. فتابعوا هذه السلسلة أول بأول وعملوا لها حفظ حتى يأتيكم كل جديد. والسلام عليكم ورحمة الله وبركاته.